Hello everyone and welcome to another Stat 437 lecture video. In today's video we're going to be talking about some of the theory for discrete time to event data. So in the last lecture we presented these concepts conceptually, and in today's lecture we're going to be working through sort of the full derivations, look at the mathematical details, try to look at everything a little bit more rigorously. So we're going to see those hazard estimators that we saw. We're going to see the survivor function estimators. We're going to talk about how we can use likelihood to, or the partial likelihood to sort of derive estimators that we can work with once we have covariates. We're going to look at confidence intervals, inference, all of that kind of thing. And so as always with these videos, I have a full set of notes that goes over everything here in a little bit more detail posted to the course website, so I'd encourage that you check that out. And of course, we're building off of what we saw in the last video, so hopefully this will help clarify anything that was unclear from that video. But of course, if you have any questions at all, always reach out to me. I'm happy to help in any way that I can. And so with that, we can get started here. And the first thing that we want to start talking about today is this hazard function estimator and sort of the assumptions that we're implicitly making regarding censoring time. So we saw this notation in the last lecture where at time k, we defined these quantities dk and rk. Right, so at time k, we take dk and we take rk. And dk is the number of events that happen, and rk is the number at risk. Right? And so here, we're thinking about rk is however many people were left over at the start of the interval, and then dk is the number of those people that experienced the event. And so if you condition on people still being left in the sample at time k, and you want to know what's the probability that they experience an event in this instant, well, we can just use that as the ratio dk divided by rk, right? Because rk in the denominator there is the total number that are still left, so still at risk. So that's sort of that taking care of that conditioning component. And then dk is the proportion of that had the event occur, right? And so this is what we sort of wrote down as our estimator for the hazard function, because the hazard function takes that definition. It's the probability that t is equal to k, conditioned on t being at least k. Right, and so we know that for all of these rk people, t is at least k, and this is the proportion that equals k for those individuals, right? And so this is a really intuitive, nice estimator here. And you can show, for instance, that this is going to give you, if you take the expected value here, this is going to give you sort of the correct value. But there's a few things to point out with it. And so in order to try and motivate this, what happens if someone has an event that occurs right at the moment that they get censored, right? And so, normally we're thinking about this in terms of, with continuous time, this doesn't sort of seem to be a big issue, but with discrete time, we saw this example where we were looking at teachers leaving their jobs, right? And so hypothetically, a teacher could quit in the same year that we stop following up with them. And so what do we do in that situation, right? And in order for this estimator to be valid, we've actually sort of implicitly made an assumption about it. And it's not a big assumption. It's actually a fairly reasonable assumption, but it is an assumption nonetheless, and we should talk briefly about it. So the basic premise is that if an event occurs at the same time that censoring would occur, we actually assume that censoring occurred very slightly after the event. So we still observe the event, right? And so the way that we're typically going to write this is if ti equals ci, right? Then what we do is we define ci is going to be equal to ti plus, say, where that's just some time point, sort of the instant after ti, right? And the reason that this matters for us is because we have to think about this ratio here, right? If there are people being censored and there are people who have their events in the same interval, which portion of them are going to count towards this hazard estimate? And the idea is that anyone who has that event, or we assume that we observe everyone who has the event, right? There's no one who had event and censoring take place at the same time where we did not observe it as an event. Okay? And so, again, in that example with the teachers, this makes sense. We observe them throughout that 12th year or up to the 12th year. And if they quit, we still record them as having quit. And everyone else that we didn't observe quitting, we just say, is censored. Okay? And so, under this sort of assumption, this convention on our notation here, we get this nice estimator for the hazard function. And once again, we emphasized in the last lecture, this is essentially all we did with the transition models as well. So it's hopefully fairly familiar to all of you. But once we have this hazard function, we can sort of start to do quite a lot else with it, right? And so the next thing that we talked about was this idea of the survivor function, right? And so, just to sort of re-emphasize this point, the survivor function, which we can write as s of k, is equal to the probability that t is larger than k. Right? And so what's the probability of surviving beyond this given time point here? And I pointed out in the lecture that there's sort of this parallel that we could take with the hazard function, and that's to say, at time k, we know that there are rk people who have survived at least to time k, right? And so if you take the portion rk over n, that sort of feels like that should be the survival rate, right? It's the number of people who are still at risk. And I suppose depending on how you write this inequality here, you might actually be looking at rk minus 1. But, the point stands that taking a ratio that looks like this seems like it might be a good estimator. But the problem that we have here is that this rk number is less than n for two reasons. The first is because some portion of people have events, right? So, we can sort of think about as rk, we can think about this as being sort of the number of people total, and then we could subtract off all of the people, say I equals 1 up to k, di, who had their events, right? So that's one reason that we have r k less than n. But the other thing is we have some portion of people who are being censored, right? And so this is also going to be subtract off I equals 1 up to k, and I'll just use c sub I to say the number of people who are being censored, right? Hopefully that's not too confusing because we're normally using c for censor times, but just to illustrate what the problem is here, is that if we only had this first component, right, if the only reason that rk was less than n was because of the events that had happened, then this is a perfectly valid way of estimating that probability. However, because we do have these people being censored, that becomes this issue, and we can't use this as our estimation. Now, fortunately, in the first lecture on these topics, or in the first theoretical lecture on these topics, we saw that we could write the survivor function as the product of I equals 1 to n. And then what do we take the product of? Well, we take the product of 1 minus the hazard function evaluated at I. And so, sort of exploiting this, there's this natural estimator where we can plug right into this expression, I guess that should be a k, of 1 minus h hat, right? And this gives us a really natural way of estimating the survivor function, which is sort of based on the validity of the hazard function. Okay? And so it sort of just becomes this cumulative product that we take in order to estimate our survivor function. Now, there's one thing that I would like to point out that's a little bit interesting with this, and you can end up seeing this for yourself. But if we think about what this product actually is, right? So we'll write the product from I equals 1 to k, and 1 minus the hazard function, the estimated hazard function, we saw that's going to be 1 minus di divided by ri, which we can sort of rewrite a little bit here as, so we're still taking the product, and it's going to be ri minus di over ri, right? And that product is from I equals 1 to k. Okay? And so if you think about it, at the first time point here, so we're taking k equals 1, right? What we're looking at is we take the RK is going to be N, and so we subtract off sort of the number of people who have had their event already, and it's looking at that portion. And then if you start doing this, if you say do it for k equals 1, k equals 2, k equals 3, and if you assume that there is no censoring, right? So you assume that the only reason that this R is falling is because you're subtracting off the DIs, then what you're going to find is that actually this estimator becomes the same estimator that we were discussing right here. This one, which is not valid in general. But if you don't have censoring, this estimation procedure works out to be sort of exactly the same as that, okay? And so I would encourage you to write out the first few terms here. It should be fairly quick to see that, noting that, n you could write as equal to R1. So the number of people at risk are the same number of people who are at risk of failure at time 1, right? And if you take all of your c's to be 0, you should see that this is just going to work out to be the ratio, okay? And so this sort of becomes a nice way of confirming that what we're doing seems valid. Now, the nice thing about both the hazard and the survivor function in this way, and it follows from the hazard function directly, is that all we need are these counts, right? If I give you a table and I say, we have some time period, and then we have the number who are at risk, and we have the number who have their event, right, at time t, then by just filling out this table, you can actually give me the hazard function estimated, and also you can give me the survivor function estimated. So the nice thing about this sort of framing is that from this life table here, we can actually sort of get the entire estimated values. We don't actually need to see the data itself, we just need this nice summary of the data. And in fact, if you know the total number, and you know the number who are at risk at each, the number of events that happen at each time, and you know how many people are censored at each time, then that's actually all of the information that you need as well. So you take this for t equals 1 up to, say, capital K as the end. Right, because here, we know that the number of people at risk at the next interval are going to be the number of people who are at risk at the present time minus the number who have the event minus the number who are censored, right? And so you can sort of fill out this whole life table just by knowing how many people did we start with, at each time, how many events were there, and at each time, how many people were censored. Okay, and because of that, we get this really rich way of summarizing the data where we can just list off this table. And if you're in the discrete time setting, then typically you don't have a lot of time points, and so it actually becomes really quite nice to see these tables operating. Okay, and so that's sort of how we deal with this non-parametric survivor function estimation. The next piece that we sort of talked about was this idea of measures of central tendency and trying to think about why the mean does not work. All right, so the 2 points that we want to make here are first, how we use the median, and then second, we want to talk about why the mean does not work. And so I'm actually going to go in opposite order here. I'm going to first start with the mean. Okay, and so what I want you to think about is, let's say that we have a number of individuals here, right? And so what we're thinking about is time is moving along this axis here, okay? And each individual is going to be observed for some period of time, right? And so you can think we have all of these different people. Some of them are observed for a short period of time. Some of them are observed for a long period of time, whatever. Right? Now, some of these people are going to be censored. Some of them are going to be observed with the event. And so, for the sake of this example, let's just assume that we're censoring sort of at this point here. Okay, and it's just a fixed censoring time. Now, I want to think about trying to estimate the mean survival time here. Right? And so here's the problem, is for this first person, we observe, time 1. For this person down here, we observe time 2. But then for both of these other individuals, we only, both of these other individuals, we only observe the time c, the censoring time, okay? And so the problem becomes is if you're thinking about what is the average that we could compute, well, if we take t1 plus t2 plus c and we divide by 4, right? Well, we know that this is going to be less than what the average actually should be, right? Because we see that both of these times are after c, right? And so then, what else might we be able to do? Well, if we were to, instead of doing that, we say, well, we don't actually observe the time for these individuals, and so they're censored. Well, the problem here is now taking this average is we've actually even pushed it even lower, right? Because all of the long living individuals are discluded from our sample, and so we have the sample bias. And of course, if we're censoring at some fixed point in time, and we take the average of the people who did not live up until the censoring time, of course that average is going to be too low, right? And so means in this case, or at least non-parametric means, don't really mean anything. Okay, and so because of that, we need alternative ways of capturing these measures of central tendency, and the obvious one to choose is the median. And the reason that the median is the obvious one to choose is because, at least theoretically, the median is defined as the value m such that the survivor function is 0.5. Or, sort of more correctly, in the discrete time case, we need s of m to be greater than or equal to 0.5, and we need s of m plus 1 to be less than 0.5. Right? And so because of this, we're looking for some value of m that this sort of corresponds to. And then the idea is that, we can sort of just read off what's that value of m, right? Because we have those live tables, we have our survivor functions, we know how to estimate them. All of that works out nicely. But the issue becomes that really the median that we care about is somewhere between m and m plus 1. And so you could kind of just report that, but what we like to do instead is we like to think about sort of doing some sort of interpolation here, right? And so if we find that value of m, you can start with that, and then we say, well, it's actually going to be a little bit more than m. And how much more than m? Well, we can see how much too big was it, right? So this is how much did we overestimate that value of m. And then we sort of take that as a portion of how much does the actual value change between m and m plus 1, right? And so the idea here is that if you think about connecting s of m and s of m plus 1 with a straight line, right? Think about the survival portion of those connected linearly, then what this gives you is this is the proportion of the amount of time sort of that exists between those two. So to make this a little bit more clear, right, at, let's say we have some sort of plot here, right? And so we're going to have a value m, and we're going to have a value of m plus 1. And because this is discrete data, what we have is we're saying maybe up here we have, say, 0.55 at m, and then maybe at m plus 1, we're down here at, say, 0.49. Okay? And so we know that the median, the true median, falls somewhere between m and m plus 1. Okay? But we don't know exactly where. But looking at this, we know that it should be a lot closer to m plus 1 than it is to m. And so the idea is if we take this 2 points and we connect them with a straight line, well, we know that the sort of run of this is the size of 1. And so the rise of it is going to be this sm minus sm plus 1. And we want to know where along this straight line is 0.5. Okay? And the idea is that 0.5 along this straight line falls at the proportion of sm minus 0.5 as a proportion of sm over the total distance that's traveled there. So you're sort of just doing that linear interpolation there, and by doing this, this gives us a closer value, right? And so in this case, you would end up with m plus whatever that would be, 0.05 divided by 0.06, right? So m plus 5/6 essentially. Okay, which makes sense because that's a lot closer to m plus 1, which is what we said it should be. So that's the idea of using the median for central tendency, using the linear interpolation to get sort of a more accurate version of that, and discussing why the mean is going to always be biased downwards when we have censoring in our data. The next thing that we want to discuss is this idea of the assumptions that are related to our likelihood derivations, and sort of more specifically looking at how we can simplify down the likelihood expression based on everything that we've seen. Okay, so to recap slightly, we wrote down that the likelihood is going to be the product from s equals 1 to infinity, the probability of ys zs jointly, and then we condition this on sort of the joint history yz of s. Okay, and here, what are we looking at? And I should suppose that this is technically the likelihood contribution of a single individual here, but we'll sort of drop that notation for now because it's not helpful to hold on to. The idea is that ys is a stochastic process that takes the value of 0 up until the event occurs, right? So that's going to be a value in 0, 1, and ys equals 1 means that the event occurred. Then we also take zs, which itself is going to be a stochastic process with values 0 or 1. But here, zs equals 0 means that censoring occurred. Right? And so we have ys as the event process, we have zs as the censoring process, and the idea with the likelihood contribution is that we want to model these two things, right? And so what we can do is, instead of writing it out as this joint probability here, we can write this as a conditional probability, right? So this could become the product from s equals 1 to infinity. In the first term, we want to just have a ys, which means we need to condition on that zs as well as on the joint history. And then we multiply that by the probability of zs, and here we're conditioning just on the joint history, right? So there we're just using sort of the definition of a joint distribution based on the conditional decomposition. And so this likelihood right here is actually a fairly complicated likelihood, right? So this first term, we have to come up with some model for whether or not the event occurs based on the censoring process as well as the full history of event occurrence and the censoring occurrence. And then the second term is just about the censoring process, right? So we need to be able to model when is the person likely to be censored based on sort of their history. So there are two ways that we want to try to simplify this. And the two ways that we want to try and simplify this is sort of shown based on these two terms, right? So in this first term, what we don't like is that we have to condition on the censoring process. And what we don't like is that we have to condition on the history of being censored. And so what we say is, well, what if there's conditionally independent censoring? What if the probability of ys given zs, this history vector here, what if this probability is exactly the same thing as probability of ys and then just conditional on the history of y? What if z is nowhere to be seen, assuming that we know the full history? And part of why we make this assumption is because it seems reasonable, right? It says that if you've observed their whole process of whether or not the event has occurred, we don't need to know whether or not they've been censored, right? It's independent, assuming that we know that much. And that feels pretty reasonable. But more why we like this is because now this first term has become only dependent on the event process, right? It's totally separate from the censoring process. And the reason that we really like that is because if we can figure out some way to make the censoring process less meaningful for our inference, well, then we're working with something that's already sort of really simple for us to think about. Okay, so that's the first assumption, and we call this conditionally independent censoring. And based on the likelihood analysis that we're doing, conditionally independent censoring is entirely required. If we don't have conditionally independent censoring, none of what we're about to talk about works. It's going to be biased, it's not going to give you valid results. So you need to make sure that it's valid to say that things are conditionally independent based on censoring. If you can't say that, there's one other thing that we like to do, and this is going to help with our efficiency. Right? And so just to clarify how we've already managed to simplify this likelihood slightly, what we can do is under the assumption of conditionally independent censoring, we can come in, we can remove this first term, and then we write in just the probability ys given this history of y, right? And so we can already see we've made this quite a lot simpler here, and it's nicer to work with. But it's still not, beautiful to work with. There's still quite a lot going on here. And so the second assumption that we like to do is one of non-informative censoring. And so the idea with non-informative censoring is we have these two terms here. We have this probability about the event process. We have this probability about the censoring process. Each of them are going to have some parameters that define them. And if we say the parameters that define them are not shared between the two of these, then we can think about them as being functionally independent, right? So information about the first process doesn't tell us anything about information about the second process. And if that's the case, well, because we're just using a likelihood analysis, what you can do is we can think about just defining likelihood as sort of being proportional to. So for the sake of clarity, let's suppose that this first model here, this model about the event process, is characterized by some parameter theta, and this second process is characterized by some parameter phi. Okay? Now, if phi and theta don't share any components, they're entirely separate from one another, then what we're looking at is we're looking at this as being sort of the likelihood of theta and phi, but we only really care about the likelihood of theta. We only want to make inference about theta. We normally just, censoring is an inconvenient thing that happens, but we don't really care about predicting it. And so we just want to know what the likelihood of theta is. And because this second term does not have anything to do with theta, what we can say is that the likelihood of theta is going to be proportional to this product, s equals 1 to infinity, of only this first term here. Okay? And so why does this matter? Well, it's not going to be exactly equal to that. We're going to need to have some sort of, normalizing constant here. But that normalizing constant doesn't tell us anything about the parameter theta. So once we differentiate with respect to theta, the fact that this other piece here has no theta in it goes away. It's just not something that we have to worry about at all. And so because of this, we can use that non-informative censoring to really simplify this down to be something that is really straightforward to work with, right? Now, if it's not the case, well, it's still technically true that our likelihood is proportional here. The problem is that, if this depends on both phi and theta, for instance, well, then there's information about theta in the second term. And we're not going to find that it's biased if we just use this sort of squared off version here. But what we are going to find is that we lose efficiency. We would have better, lower variance estimators if we included both terms, right? So conditionally independent censoring, necessary assumption. If it's violated, we're not going to end up with unbiased estimators. Non-informative censoring, on the other hand, not strictly required, but it does help ensure that our estimators behave nicely, that they're nice and efficient. Okay? So then what we can do is we can take this likelihood expression here, and we can realize, well, I guess actually first to fix a small mistake that I have here, we're no longer taking the product up to infinity, we're now taking it up to the time that we're censored at, right? And the idea there is just that these terms are not actually contributing anything to it. The other way that you can think about this is that after CI, this probability is exactly equal to 1, right? And so just to keep things nice and simple, we write it like that. But so then the question for us becomes, okay, what can we actually do to work with this likelihood, right? And so the idea is, how do we model this probability that ys equals 1, say, given the history of ys? And, given all of the notation that we've been using, and given the fact that our product stops at ci, well, this is just going to be probability that ys equals 1 given the probability, or given the fact that ys minus 1 is equal to 0. So it's the probability that the event happens, assuming that the event has not yet happened, right? And what you should see here is that this is actually equal to h of s, right? This is the exact same thing as saying, what's the probability that t equals s given t is greater than or equal to s? The event has not yet happened. What's the probability that it happens right now, right? So this term that we have right here is exactly equal to um, our hazard function. And so in the interval where ys actually becomes 1, we have this contribution of the hazard function. For all of the other intervals, what we have is a contribution of 1 minus the hazard function, sort of by the same rationale, right? The probability that ys equals 0 is 1 minus the probability that it equals 1. Right? And so pulling these terms together, what we see is that this likelihood contribution for individual I, which we've been writing as the product s equals 1 up to ci, is going to be given by hi of s to the power of yi of s, right? Because if yi of s takes on the value of 1, then we want the hazard function. And otherwise, we want 1 minus hi of s, and we're going to put that to the power of 1 minus yi of s, so that here we take what we were just talking about right here. If yi equals 1, we get this. And if yi of s equals 0, then we get this. Right? And so this is the likelihood contribution for one individual. And then, of course, to do it over the sample, what we would want to do is we would want to take this, and we'd write this as the product I equals 1 to n. And that's our full likelihood now. Okay? But so taking a look at this very quickly, if we were to re-express this ever so slightly, where instead of this yi of s notation, if we just recognize that that is a binary indicator, and then hi of s is a probability, well, this is just the binomial likelihood function, right? If you have a binomial random variable with probability of success being hi of s, this is exactly what you would get as the likelihood there, right? And so what this tells us is that we can start to use likelihood theory to start modeling this. And in particular, what this means is that if, for instance, you specify some sort of probability that yis equals 1 given, say, xi, where xi is some set of covariates, well, now we can start to use logistic regression to model this. And that's exactly what we're going to do in the coming lectures, right? But so the reason that all works out is because this likelihood expression that we get right here, it's the binomial likelihood expression. Okay? So the last main topic that I want to talk about in this lecture here is this idea of building confidence intervals for our survivor function. Okay? The confidence intervals, if we, for instance, are thinking about having fit this hazard function using a GLM, right? Well, we can use the GLM for the hazard function. However, to do this for the survivor function is a little bit more challenging. And the reason it's a little bit more challenging is because we're using a product, right? And so to convert from the hazard function, which is a nice object for us to work with, to the survivor function, we have to take this cumulative product, and each of those individual terms is being estimated, and so it becomes this sort of big mess to try to do. And so we have this nice process which revolves around an application of a delta method, and because of that, we can sort of get confidence intervals out. But it's not necessarily the most straightforward process, and I don't expect you to necessarily be able to do the theoretical work here. But what I'm going to do is try and talk through the process, talk through the motivation of the process, and then from there, this is how we can sort of get out intervals, right? So the idea is that we've estimated our hazard functions, And moreover, we also have, say, through using GLM to fit the hazard function, we also have a variance estimate for, say, the parameter alpha hat. And what we're saying is we're saying that the hazard function is some function that relies on alpha hat, okay? And so the idea here is that, we've used a GLM based on this likelihood expression. We've used a GLM, we've fit this hazard function, and now we have an estimated variance for our parameter from the GLM as well, okay? And so the first step is that instead of looking at the survivor function directly, we want to look at the log of the survivor function, okay? And the reason that we want to look at the log of the survivor function is because the log of the survivor function becomes a sum. It's the sum from I equals 1 to t, and then we take the log in each one of these terms as 1 minus h hat of I. Okay? And so already here, if you're thinking about trying to work with these expressions, working with summations is a lot easier than working with products. Okay? So then what we do is we make this observation. And this is an observation that, you could derive for yourself, but I'll sort of just state it for you here. The idea is that the variance of this set of log survivor functions, so let's say log s hat of 1 up to log of s hat, and say c as the maximum value there, right? Well, this is going to be approximately given by what I will describe as, say, g hat times by the variance of alpha hat times by g hat transpose. Okay, and what's this g? What is this g matrix here? Well, the matrix G is given by the lower triangular matrix, where we take negative h of each term, and so then we'd go h1, negative h2, negative h1, negative h2, negative h3, and sort of so on, right? And everything up in the top there is a 0. Right, so it's this lower triangular matrix. And, where is this coming from? Well, more or less where this is coming from is thinking about differentiating this expression here. Okay, so that's sort of the idea of where this is coming from. But, and so then the idea is that in each of these rows, well, our variance is going to sort of depend on increasingly many of these hazard functions. Okay, but so with this relationship, if you take this relationship for granted, well, then what we have is we can say that there's approximately normally distributed confidence intervals using this sort of estimation here, where again, this is estimated from our GLM, for instance. And so using this result here, this variance result, what we can say is that we have sort of walled type confidence intervals for the log of our survivor function, right? So then step 3 would be that we could take log of our survivor function plus or minus, 1.96 times by our standard error, where the standard error is coming out of that right there. And then the final step is that to get back to the survivor function, we just have to take e to the log s hat, right? And so this 4-step process here, where first you look at the log, we then exploit the fact that the log is a little bit easier to work with and we can derive this variance. Again, that's not something you're expected to be able to do, but through this result here, allows us to build confidence intervals for the log. And then from that, we exponentiate and we get back the confidence intervals that we want to work with. Okay? And so that's going to be the process for building confidence intervals for the survivor function in this case. For building confidence intervals for the hazard function, we just use our standard GLM tools, right? The exact same way that we were doing with those transition models. And so with this, we sort of, we've seen how do we estimate the quantities that we care about. We've seen how can we start to perform inference on those quantities that we care about. And hopefully by now, sort of this regression framework, this ability for us to answer questions by fitting models like this is starting to become somewhat second nature for you, right? This is sort of the entirety of what we're going to be discussing with respect to discrete time survival analysis. We're getting really close to the end of the course here, but I want to move on to continuous time survival analysis fairly shortly. So what we're going to do is we're going to take a look at these results being implemented in R. We're going to, get to run through them once more. I'll focus into providing a good explanation for how we go about implementing these confidence intervals for the survivor function. And you'll see, how can we actually estimate these things from the life tables, but then also, this GLM that I've been talking about, where we exploit the fact that we have our binary likelihood right here. How can we actually fit those GLM models, right? And so if you're confused about any of this, please, of course, ask me questions, but also in the next lecture, you'll get to see all of this once more as we walk through an applied example. So hopefully that all made sense, and I will see all of you in the next lecture.